Okay, so this is another video, just a little bit more practice on using delta H hydration, delta H solution, and lattice enthalpy using that energy cycle we had before. Here the problem is slightly different though. Instead of us working out delta H sol, they give us delta H sol. What they don't give us is they give us all the information. They give us hydration of the sodium, they give us a lattice enthalpy of sodium fluoride, and we've got to work out the hydration of the F- ion. That's what we've got to find out. So we're going to use the same energy cycle. So we just put Na Na gas, fluoride ion gas, going to form sodium fluoride solid, right? The ionic lattice. So this is going to be the lattice enthalpy up here, isn't it? So that is minus 918 kilojoules per mole. In that direction, it's exothermic. Down here, we're going to have the ions when they are in aqueous solution. There we've got, right, this is what we've got to, that is usually what we've got to find out, but not in this case. It's delta H sol, and that has got a value, they tell us, of minus 12 kilojoules per mole. Minus 12 there. And then on this arrow, we have got the hydration of the sodium ions, which they do tell us is minus 406, and delta H hyd of the F- ion, which they don't tell us. Let's say that's equal to X. Okay, so let's do it this way then. So right, Hess's law, we're going to go from there to there, and the other way of doing that is going around the long way, around like that, isn't it? So if we do that, we get minus 918 is equal to, we're going with the arrow there, so it's minus 406 and minus X. Let's say that plus X, we'll have that plus X, we don't know what X is, yeah. And then this arrow here, right, we're going against the arrow there, aren't we? So we need to reverse that sign, so that becomes a plus 12. Okay, rearrange all that, we get X is equal to minus 524. So we can say that the delta H hydration of the fluoride ion is equal to minus 524 kilojoules per mole. So nothing really different there, just slightly giving us slightly different information. Got to find out a different unknown. Right. Just just want to talk now a little bit about what we were talking in the end of the last video, which was the insolubility of silver chloride. Sorry. Right. So we're going to have a look at all of the halides here, right? Now, what we have got is, right, now we should know that, remember what we can say about the solubility of these. If these, silver chloride, bromide, and iodide, they are all insoluble, aren't they? Yeah, and that's how we use the test. We test for the presence of chloride, bromide, iodide ions by adding silver nitrate, and we get a precipitate because we're insoluble. And if you remember, a silver fluoride is actually soluble. So I'll write that down there. That is soluble. This is insoluble. And these are all insoluble. Now, if you can remember, you probably appreciate that silver iodide is less soluble. It's the least soluble of the lot. Okay, as you go down there from silver chloride to silver iodide, solubility decreases. Okay, nothing is truly totally insoluble. You'll always get a tiny bit of it dissolving. So if you think of it as an equilibrium, you've got Ag X solid going to Ag plus aqueous, and X minus aqueous. And really, it's a matter of how far this, we know this equilibrium is very far to the, is in this way. The equilibrium lies in this direction. And the more insoluble something is, the more the equilibrium lies over to the left. And silver iodide is the least soluble of the lot. If you remember, you try and dissolve it even in conch ammonia, that precipitate won't dissolve. Whereas the silver bromide, you remember, that would dissolve in conch ammonia solution. And the silver chloride, you can get that to dissolve by adding dilute ammonia. So we've got a trend going down the, we've got a trend as we go down the halides of silver in solubility. What we're going to try and do now is we're going to find out, do we have a trend in delta H? Do we have a trend in delta H sol as well? Okay, so we're not going to work out each one individually because it'd take too long, but I'm just going to, so we want to find out delta H sol, don't we? Yeah. Right, so from that, and I've color coded that, so delta H sol is going to be equal to, using Hess's law, I'll do that symbol in black, I think. Right, so we're going to have to go around this way, aren't we? Let's think we're going to go around that way. So we've got lattice enthalpy. Now, dissociation is positive, so this way is going to be negative, isn't it? So it's going to be minus lattice enthalpy. I'll put that down. Minus lattice enthalpy, going against the arrow. Here we're going, so it's plus delta H. I'm going to do that in purple because I've done it there. Delta H hydration of silver. So it's plus delta H hyd of silver. And it's going to be plus delta H hyd of the whichever halide ion, I'll call that X. Okay, so the size of delta H sol is not dependent on this, is it? Because this is the same for every single one. It's dependent on the lattice enthalpy, and it's dependent on the hydration of X. So the size of it depends on that. Right, now as we look down the lattice enthalpy, you can see that the lattice enthalpies, they decrease slightly. Okay. Whereas, all right, so that's one variable to think about. The other one is the hydration of the halide ion, which is in red here. Now they don't decrease slightly, they decrease a lot, don't they? So that means that delta H sol, as you go down, because the lattice enthalpy isn't changing much, that doesn't change much, this changes quite a bit and it becomes less, okay, or it becomes less negative. So that means as you go down the group, delta H sol down the group becomes less negative, it becomes more positive. In other words, becomes more endothermic. And I've just worked, you can work them out for yourself, but if you want to work out what they are, delta H sol, let's just put the halide down here. So I've got AGF. Right, so for the fluoride, you've got this lattice enthalpy here, and then you've got this very, very negative delta H hydration of the fluoride ion. And that is enough to make AGF delta H sol slightly negative. It's minus 39 kilojoules per mole. Now with the AgCl, right, the lattice enthalpy doesn't change that much, but this is a lot less negative. So that means the overall effect is delta H sol is not as negative. Delta H sol is actually a lot less negative. It's positive, it's plus 54. And the same thing happens with the bromide. So the lattice enthalpy goes down a little bit, like 15 kilojoules, whatever it is. But this goes down by more, by 30. So that means this becomes even more positive. So that's plus 70. And the trend continues with the iodide, and that's plus 108. So you can see as the delta H sol becomes more endothermic, the solids become more insoluble. And as I said, the simple explanation of that, if you haven't done delta G, is endothermic reactions usually don't happen. If the delta H is positive, the reaction tends not to be possible. That's a simple explanation. Of course, if you've done delta G, so you're looking back on this video, delta G is delta H minus T delta S. Well, delta H is positive, which makes delta G positive. So that means this has got to be negative enough to make delta G 0. And it is in the case of the fluoride. It's not quite big enough in the case of the chloride, so it won't dissolve, and it's definitely not the case of the bromide and the iodide. Anyway, I think that is all we need to do on delta H sol and delta H hydration.